Okay, my various clocks say it is the top of the hour. This is Joel Halpern with Bruno de Crane and Jim Gashard, your 3 spring chairs. We are starting the second spring session using the agenda as per posted. I hope we can manage to stay on time. We did a good job the first time, but still we want conversation and discussion. Okay, Bruno, shall we go to the replication segment slides? And Daniel, you're up.
Yep, good morning. It's Dan Voyer. I will be presenting on behalf of the author and update. Yeah, that's the slide. So last time we presented this work, it was in 2019, March 2019, I believe. Since then, we started a little bit the author list, as you can see, but we added that behind us, there's a lot of heavy contributor. I just want to call out, like I think I saw Andrew Stone and Tax had login this morning. So those are heavy contributor also behind us and behind this work. Okay, we can go to the next slide. So that's my kind of an update on the update. There are a lot of different pieces of this work that are progressing in different other working groups. And since we've been able to have working group adoption here, it unlocked the working group adoption of the other piece of work in the different working groups that are shown here. We recently, last year, also brought the MVPN one that you can see there that is adopted in the best. That's kind of an IPTV type of use cases for the people that run MVPN there. We recently also added the last one there is the ping, like a way to validate the tree. It's fairly new and it's been pushed into the ping working group. The PCE is under conversations. We're progressing there too, and the IDR is also something that we're progressing as well. We can move to the other slide. Okay, so really the update here is that it's very simple. We just decided to add this IETF to the replication segment. And more precisely, we added like the N replicate function that you can see in the first paragraph. But the essence of, and in compliance to the network programming framework that is now an RFC. But really what it means is nothing different than the mechanics brought up by the SR-Mpls version of the draft. Like the first 3 versions covered the SR-Mpls here. And really what's new here in the context of the replication is really an encapsulation function that is done at the root node to encapsulate the SR-VSS replication. So that is the N replicated function. Now that works exactly the same as it is in the SR-Mpls, where you have the replication SID label that is associated to a replication segment that somewhere along the side of the network will hit the replication node, will decap, and then process to the host. So really nothing really different from a mechanic perspective. We can move to slide 4. All right, so more specific about the N replication function here. So that's a function that is local to the replication node. As you can see, it is associated to the replication SID that will serve in replicating the data towards the leaves. I have an example coming. It will enable, it is enabled on the node where it will replicate the incoming traffic towards the leaf or the destination IPv6 host. That's pretty much what it is. It's exactly the same as the Mpls, as I was saying. At the leaf, it will perform a decapsulation and then forward the traffic directly to the end host. Now we can move to slide 5. Now the text bottom top left is the semantic about what's going on with the drawing, and then the bottom right is really what's happening in this example. This example it's the one that, just to stay current with what was presented by Uman at the PIM working group, it's the example using the three topology to explain this example. But there's also another way we can do the same thing, which is the spray model. Now we just chose to use the tree version, and it's pretty easy to follow with the text that we've put there. So basically, the node 1 here is the root, and then the node 2 is the replication point. Node 5, 6, and 7 are the leaves. And then node 3 and node 4 are just transit node. They, in the context of SRv6, they could be just IPv6 node, and then it will go through the routing extension, the routing header. So they don't do anything with node 3 and 4 in this context. At node 2, it will replicate towards the leaf 5, 6, and 7, and then at 6 and 5 and 7, it will decap and remove the SRH and then forward the traffic directly to the destination, according to the IPv6 destination address. And that's pretty much it. We can go to slide 6 and open for question. Well, I hope you were able to hear what I was saying, that beautiful speech, and I was not on mute or something.
You were audible, Daniel, and understandable. No problems. I'm not seeing anybody in the queue. Going once, going twice. Let's move to midpoint protection. Heimo, you're up.
Hello, everyone. Can you hear me?
Yes, we can. Thank you.
So today, I'm going to talk about SRT midpoint protection. Next page. So in this latest version, we updated the section 1 introduction, and we also made some editorial changes. In this updated document, we described the problems we're going to resolve, and also compare the difference between our solution and the other existing solutions. First, let's look at the problem we're going to resolve. When node N fails, its upstream node P as a PLR will do the fast reroute. So in this case, we provide protections for the node N failures. However, after the IGP convergence, the other nodes will remove the routes to node N because N is failed. For example, node B, after IGP convergence, B removes its routes to node N. So from this point, the traffic will get dropped until a new SRT routes or path to C is installed. So we can see from the point IGP convergence until a new path is installed. During this period of time, traffic will get lost. So our draft will propose a solution to resolve these problems. So the rough idea of our solution is that for any node such as P, if this node can provide capability to do the proxy forwarding, then this node will advertise its capabilities. So all the other nodes will use the routes to the capable nodes after node N fails. For example, node B will use the routes to P for node N's cease after it fails. So in this way, even BGP after BGP convergence, and then we can still provide protections. That's roughly our solution. There is another solution which is adopted last year, which is called Spring Segment Protection SRT path. So that's informational. So the idea of that draft is that for every node or for some node, they will provide some extra functions. The function is that the node will accept some kind of configurations. For example, is time configure a time. During this time, we'll hold the routes, all the routes, to node N. So if that node supports that functions. So after configuration, and then if all the nodes in the network can provide this function, and then hold off the routes for some period of time, even that node failed, and then they can provide some the protections. However, if some of the nodes do not support these functionalities, and then we may not provide protections during this period from IGP convergence to the new route, new path is installed. So our solution provide enhancements to the existing solutions. So let's look at more details. The next page. So basically, our solution provides more coverages, and in addition, our solution also provides protections for the binding segments on a node when that node fails. So first, because for each of the node, if that node can support proxy forwarding, and then that node will advertise a capability for that functions. So all the other nodes will receive this capability for those nodes, and then it will send the routes, send the package to the least capable nodes when one node fails next to that node. So this may provide more protections, even though some of the node doesn't support the functions.
Okay.
So we provide.
Just a moment. Shraddha's been trying to ask a question, and I'm not sure which slide it's on. So, Shraddha, can you ask your question?
Yeah. So my question is that, so you mentioned that in the previous slide you mentioned that the draft IETF Spring Segment Protection SRT paths has provided a solution, but you are pointing out that because that draft is informational, so somebody may not implement it. So are you suggesting that draft should be made standard? Do you think that will solve the problem, or what is the?
No. That's not a problem. I mean, the problem is that if some of the nodes do not support your draft, right? So even though you use a standard, and then maybe some nodes don't support your function, and then some nodes may not support your function, right?
Yes. So if some node does not support this function, then it may not. The behavior of the network won't be any worse than not having supported it to having supported it, right? So so the solution is to make that node to support this draft. Is it so I see that you are proposing an alternate where there is a proxy for every node. There is a proxy. So to me it seems like it has a lot of operational overhead. So now operator has to configure which node is a proxy for which one, right?
No, not that way. So this one just as soon as that node have capability, and then for all its adjacent node, and then it will advise that capability in one bit. Don't need to configure. For example, for P, we just configure this one is capable. And then we don't need to configure this P is capable for N, for N1, and then for P1. No, just configure this is capable, and then P will advertise one B, one flag, indicate that P is capable to do the proxy work.
Yeah, so I'm not able to get what is the
Shraddha,
advantage. So the problem you pointed out is if B doesn't support draft IETF Spring segment protection SRT paths, then it's a problem. But if B doesn't support this midpoint failure draft, it's the same problem, right?
This can do more because, for example, we know which node is capable, and then we can send the traffic along those nodes which are capable, and then we can, even so we have some nodes don't support this capability, and then we can provide more coverages compared to just keep the old routes to node N when node N fails.
I think we need some discussion on the list on this because I'm having trouble parsing whether the real difference is the capability flag or whether there's a real difference in the solutions. And no, I don't want you two to sort that out right this minute, but I do think we need to discuss it with the whole working group on the list. Shraddha, that makes sense?
Yeah, it's okay. And another improvement.
Before you go on, Bruno had a question.
Okay.
Go ahead, Bruno.
Bruno speaking as an individual. I have a comment. I may have a comment on terminology, which may also help on the previous discussion. As far as I understand, we talk about protection for behavior which is pre-computed, and which is done before the IGP convergence. Whereas I understand that your proposition is behaving after or during the IGP convergence, in which case, in general, we call about restoration. So if it's a correct understanding, that would help make a distinction between the draft from IETF Spring segment protection on your draft, because one would speak about protection, while the other one deals with restoration.
Yeah, I think for the existing draft, so the other node don't know, one node don't know the other node whether they have this capability. So it just use the old routes to the failed node for some time. But our node have more information about which node is capable, and then we can send the traffic along those nodes which are capable, and then we have more chance to get the traffic to the node next to the failed node. We can provide the protections, even though some of the nodes do not support these functionalities.
Okay, is there more you wanted to cover? Because this is all of your slides and we've taken your 10 minutes.
Yeah, another enhancement is that we provide protections for the binding segments on a node when that node fails. And then I think the existing draft does not support these functions. The second bullet, big bullet, binding segment protections. So we provide those protections.
Okay, thank you. Let's move on to the next presentation on segment routing for redundancy protection. I'm not sure whether Fan or Zhu Song is going to present, but whichever you is planning to present, please go ahead. Looks like Fan. Go ahead, Fan.
Hi, thank you. This topic includes two drafts. One is the segment routing for the redundancy protection, and another one is the SRH extension for this redundancy protection. So I will cover both drafts there. Next, please. Yeah, just very brief introduction to the redundancy protection. It is one of the mechanism to achieve the service protection, and it follows the pre-off prince. So there is an example scenario there that when the flow comes to the there are two nodes. One is the read and one is the merge. When the flow is sent to the read node, and the read node replicate the flow into two copies and send the two copies from different paths respectively. And when the merge node receive the first packet of each sequence number, I forgot, on the redundancy node, and there on the R1 or on the redundancy node, there is a flow ID and the sequence number are marked there on the traffic on the packet. And when the first packet of each sequence number is received on the merge node, it will be sent to the R2, and the other packet means the redundant packet will be dropped. I will give more explanation about this procedure there later. Next, please. And to support the redundancy protection, that we define this several new things there. And first is the redundancy segment. It is a new segment defined for the redundancy node, and there's also the new behavior of this redundancy of this segment is defined. The second is the merging segment. It is the segment used on the merging node, and with the behavior of this segment is defined. And to support to identify the unique flow or identify the packet sequence within one flow, that there is flow identification. The sequence number is defined there. And last, there is a redundancy policy. It is a variant of the SR policy, and it is used. It is associated with the redundant segment when the redundant segment is executed there. And the difference between the redundancy policy and other normal SR policy is it includes more than one ordered list of the segment, and all of this ordered list of the segment will be used at the same time. Next. And we have the update since the draft since last IETF. Yeah. I think actually I refined this is not the latest version of my presentation, but I will try to explain there. Actually, we redesigned the process and of course update the specification of the redundancy segment, merging segment, and the encapsulation of the flow identification sequence number, and also add some description of the redundancy policy. And yeah, we also split the segment description into two parts. One is the SR Mpls, another part is SR V6. Next. Yeah, as I mentioned, that redundant segment is updated, so it is updated as a variant of the bounding seed. If you use the bounding seed, that there you can set a whole list for the service from the ingress of the SR ingress node of the SR domain. So there's also some since it is defined as a variant of binding seed, so there is a change on the pseudocode node, pseudocode. And another big change is we decouple the replication behavior and the marking of the flow identification and the sequence number. We think that these two behaviors, one is the application, another is the marking, they are not necessarily bounded together, but it depends on the choice, on the deployment choice. I give the two choices. I give the two. I give the examples of the two choices later in the later slides. So here that but since from the actually, after we updated this draft, and we also received the comments from the from others, so we actually we define. Actually, we should refine the suit code later on, and I will not explain the suit code here because it will be refined later, and maybe we can just go to the next slide and to explain the. And also the merging node, the update is we specified how to determine the packet, if the packet is a redundant packet or not, because the sequence number is there is used to determine the packet is redundant or not. And there's a suggestion that to use it to look up a local table there, but it's not. Yeah, it just give an example that the sequence can be done in this way to determine the packet is redundant or not. Yeah, next please. Here we take the SRv6 as an example to explain the process of the redundancy protection, and I give two choices, two options there. The difference of the two options options are whether we assign the flow ID and to generate the sequence number at the ingress node of the SRv6 node, or at a specific redundancy node. When the redundancy node is not the first node, not the ingress node of the SRv6 domain. So if we in this option that we assign this flow ID and generate the sequence number at the ingress node, and it is not the redundancy node, so this information will be kept as the optional TLV in the IPv6 header, and the packet is transmitted to redundancy node, and redundancy node is triggered is a bounding seed, and this so it added. So if the bounding seed used with the encapsulation mode, and there will be another IPv6 header added, and in this case, the segment list is the redundancy is the R node, is the R and R3 or R and R4, and because why we are not including the merging node M here, because when the sequence number and the flow ID are used in the merging node, and it will need the flow identification and sequence number in the IPv6 in the inner IPv6 header, or maybe there's another alternative to use it. You can also copy the flow this optional TLV from the inner IPv6 header to the outer IPv6 header when you do the redundancy node, when you perform the redundancy segment. It just to see there are actually different choices, different options to define this to make this redundancy protection work.
Okay, before you go on to the next slide, Fan, Greg seems to have a question focused on this material, so it would be good to let him ask now.
Sure.
Greg, go ahead.
So, if I understand correctly, what you're proposing support packet replication duplicate elimination function. As part of this, in the DepNet group, there is a functionality order preservation. So is it something that as well you expect that merging node will do order preservation based on the sequence number?
In the current draft that we define this ordering as the optional function. Currently, we are focusing on the replication and elimination part. but I think that is some work that we can do after we finish the first phase.
Well,
Greg, if I may for a moment, that does raise the more general point that given the overlap in functionality between this and the DET network, we need to make sure this is coordinated. I'm not saying it has to be done there. I'm saying it has to be coordinated, though.
Yes,
Go ahead,
and
Greg.
actually, that's why in my comment I added DetNet to the distribution list. I had a question to this draft and send this on the list. So you implement something which is more advanced than 1+1 protection. So why do you think the complexity of pre-op function has a benefit comparing to 1+1 protection? Because 1+1 protection is much simpler. The merging node selects the working path, and one path is backup. The redundancy node sends data on both paths, and the merging nodes picks up data only from working path. If the working path fails, it switches to the other feed. Here you do packet by packet selection from 2 or more paths, but it comes with a lot of complexity.
Yeah, but actually, I've never compared these two together because they are actually different mechanisms. Yeah, I cannot give you some comparison result about this because I've never considered they are the same or they have the same effect. Yeah, but I think maybe we can discuss it in the mailing list. Yeah, currently have no answer there.
Yeah,
Okay.
thank you.
Fair enough. Ron? Ron, if you have a question, ask quickly. Otherwise, we're going to move on to the next slides.
I was on mute. This proposal makes the merging node stateful. The merging node has a finite amount of memory to maintain that state. What happens when that memory gets overrun?
What specific state do you mean? I mean the state of the packet?
Well, for
Yeah,
every
when you compare.
whether it's seen a copy of it before.
Yeah, I think that you mentioned there's actually there should be a sliding window there. I'm not sure if you mentioned that it is related to the sliding window, that how you compare the how you compare the sequence number with within the amount of the packet, right?
Well, there is some policy stuff on later slides. Ron, I think we'll need to go into more detail on this on the list. Mark, quickly, we're running over time. And I want to give Fan the time to cover the rest of her slides. But go ahead, Mark.
Okay. I think there's supposed to be a controller to configure SR policy on the merge node. So it should know what's the ability of the merging node. So it will not let the merge node overrun if the memory cannot support so many flows. So I think there need a way for the controller to configure whether how many flows I can support on the merging node.
Yeah, I agree. I think that is something because this draft is only cover the data plane part. I think they must have some extra. They will have some specification on the part that when about the issue that Ron raised. Yes. Next, please. So it is the updated one. Okay. Yes, the second option is the difference is just when where you assign the flow ID and the sequence number, because in this option that the flow identification and the sequence number is only used between the R node and M node. So that the two choices that you can use this redundancy protection. Will you use it from end to end, or you use it as a part of the as a kind of service. Next, please. Yes, and the second, there's another draft that we specified how the flow identification and sequence number are encapsulated in the in an SRH optional TRV. So here we give this this proposal there, and from the feedback from 6men that they think that we should change this draft back to Spring, because Spring has already can give these can have the power to give us the allocation of this optional SRH optional TRV. Next, please. Yes, here with that, actually, we define this redundancy policy and through the tuple that there is a redundancy node and redundancy ID and merging node. There are some more details about this the specification of the redundancy policy. Yeah. Next, please. I think. Yeah, actually, from last since last IETF that we have already refined the solution, and then we come back with the options of the solutions there, and we try to refine this solution and also specify the SRH encapsulation. Yeah, I think next step we'll specify the redundancy policy, another draft with more details, and. Yes, and we seek for the collaborations, like focusing on the segment specification in the SR Mpls data plane, and also there are some discussion has already been raised there in the mailing list about the flow identification and sequence number. I would like to continue with the discussion there.
Okay, Greg. You have a further question? Go ahead.
In regard to your plans to do in SR-MPLS, I can point to DetNet or in MPLS data plane that it already supports packet replication, duplicate elimination, and order preservation function. So I think that probably better to do discussion in the DetNet working group. Thank you.
Okay, Zhu Shang. Go ahead.
Next question. The first one is about ordering function. Actually, we have already considered that because it has already been defined in DetNet. In this version, we won't include it because for the simplest case, the ordering is not necessary for merge node. So perhaps in the following versions, we can include the ordering functions to cover more scenarios. And the second question about the 1+1 protection, actually, this redundant protection can provide a more provide service for more ultra high requirement applications, because there is no packet loss when the flows is switched from one path to the standby path. So that can satisfy the requirements for more maybe strict applications. Okay, thank you.
Greg, if you want one more, go ahead, and then we've got to move on to the next presentation.
That I agree that packet replication functionality minimizes the packet loss. It might not eliminate it completely, And that's basically the idea why DetNet supports packet replication function. But it comes at a cost. So that's why I brought it up in my earlier comment, so that compare the cost and then versus the benefit. And as Rowan correctly pointed out, it does create a state in emerging node, because especially if you are doing order preservation and packets can be reordered, so that comes with a lot of complexity. Thank you.
Okay. Zhushang, I don't think we can continue this conversation. We're at twice the allocated time for this, so we need to move on to the next item on the agenda. Yes, Strada's coming forward, and Bruno, if we can switch to the Seamless SR presentation.
Yeah, so my name is Shraddha Hegde from Juniper Networks. I would like to present Seamless SR updates to Seamless SR draft on behalf of my co-authors. So we've presented this in IETF 108 and 109, and we got a comment that so the draft had 3 sections: use cases, requirements, and solution. So we got a comment that the use cases and requirements should be a separate document. So in 05 version, we split the document into 2. One document is covering use cases and requirements, and another document is covering solutions. Next slide, please. Yeah, so the first one is talking about the requirements and use cases. The second one is about the solution. Next slide, please. So just a recap of the basic motivation for this Seamless SR architecture. So when the large networks organized into multiple domains, and seamless Mpls kind of architecture gives an end-to-end path across these multiple domains using BGP LU. So evolving requirements, need multiple end-to-end paths between 2 endpoints in these multi-domain networks, and Seamless SR is trying to address that. And the solution that Seamless SR is focusing on is a completely distributed solution. So where there is no single entity which has the database of all these domains and computes the path. It's more of a distributed solution where the paths across these domains get stitched together. So in terms of requirements, so we have reorganized the use cases and requirements section and clearly laid out the requirements, categorized the requirements into multiple categories such as AS and domain requirements and SLA requirements, merger and migration requirement, scalability, availability requirements, and so on. So just to quickly cover AS and IGP domain requirements. So these are different ways, the slide shows the different ways the domains can be organized. We've covered the most common use cases. It's not an exhaustive list of all the types, all the different ways operators deploy the multi-domain networks. So the first one is where there are multiple ASs and connected via eBGP. The second one is where there are multiple IGPs and there is a common border node on which on the left side there is going to be one IGP and right side another IGP, and the end-to-end connection is via iBGP sessions. And there's a third category where there's a single AS. If you see on the bottommost right side diagram, AS1 is the AS, and there is domain 1, domain 2, and domain 3, and there is no common border node. And the end-to-end connectivity is all via iBGP sessions. Next slide, please. Yeah, so this is tunneling requirements, like underlay tunnels, what all different categories of tunnels need to be supported. I think I'll run to next slide. I've talked about it multiple times already. So next slide, please. So various SLA requirements, again, latency, bandwidth, link node and domain inclusion, exclusion, and end-to-end diverse paths. and constraint applicability to subset of domains and service function chaining is something that we cover in this section. Next slide, please. So mergers and migration requirements mainly focuses on changing networks, when evolving networks and requirements arising out of those network evolution, such as during migrations, you will have to have the interoperability with BGP-LU. And you should also have the native support for best effort paths. Like if we come up with some new extension, that should also have support for end-to-end ability to create best effort paths end-to-end. And as the network evolves, we should not have the requirement of running two different families. Option A and option B use cases, and also in case of mergers, there may be a necessity to, the color mapping may vary from one domain to another domain. So there is a need to have a ability to translate that intent from one domain to another domain. And that there is also a requirement for interop with other tunneling technologies, like ability to do SRv6 in one domain and Mpls in another domain is kind of an example. Next slide, please. So this slide lists down the scalability aspects. Support up to 1 million nodes, access low, devices having low access node capabilities, and scalable response to network events, and automatic filtering of routes on access nodes, and ability to reduce fib scale on the border nodes. Next slide, please. Yeah, we also cover other requirements like protection, end-to-end protection, including intra-domain as well as border node and egress protection. Operations and automation. And I would like more input from operators community on operations. So right now we have covered like counters and ability to do ping and trace route. It will be useful to see what requirements people come up here. I mean, if operators have to deploy this and have to debug this at 3 a.m. in the morning, what would they like to see? And give that input to the requirements document. And we also covered various ways of traffic steering mechanisms and interaction with other approaches like existing centralized approaches. So we also cover multicast tunneling requirements. Like if the network is built this way and is getting operated this way, how would the multicast tunneling and what are the requirements for getting an end-to-end multicast solution? Next slide, please. Yes, so we request more review and comments. And so recently there's also another draft which is talking about similar use cases in BGP car problem statement, and we are in discussion with authors of BGP car problem statement. That's all. Any questions, comments?
Go, or I wait someone to call me.
Daniel, go ahead.
Thank you. Good presentation, Shweta. There is another SR-MPS to SRv6 document as well, which I happen to also co-author, and I wonder if you could have conversations also on your point that you're making in the next step to also try and merge and hopefully not having another design team to get together to define which one we're going to pick at the end. Would you be interested to have these conversations with on the other draft? It's SR-MPS and SRv6 interworking, the draft.
Yeah, so Dan, this particular draft is mostly covering requirements. So I would first like to cover what are the requirements in terms of SRv6 and SR-MPLS interop. Yeah, solution discussion on solution. That definitely should happen. But let's at least close on requirements. What are the requirements for? There's at a high level you can say SRv6 and MPLS interop, but it would be useful to cover the details as well.
So the car draft she mentions here is the next thing on the agenda, and I believe the interworking draft you referred to, Daniel, is the one after that on the agenda. So we will be going through all of this.
Okay, good. I'll come back then.
Okay, Cheng Li. Go ahead, Cheng Li.
Do you have any implementation or deployment of this extension?
Yeah, so what I talked about is a requirement, yeah, but we do have a solution document that that covers how these requirements stated in this document can be achieved using BGP protocol extension with BGP CT. And yes, we do have implementation and some testing going on in the lab. And this was presented in IDR as well as BES yesterday, and day before yesterday.
Okay, Zhidong, Jimmy.
I'd like to
You're
ask
up.
one. Can you hear me?
Yes, go ahead.
Yeah, my question is, can this, do you plan to support SRv6 in this architectural in this problem space?
Yes, definitely. So we have already listed as an SRv6, both SRv6 end-to-end as well as SRv6 to MPLS interop use cases. Yeah, definitely.
Okay, so the draft name may be better to change to not just list Mpls.
So the name of the draft is Seamless SR. So it covers SR MPLS as well as SR v6.
Okay.
Okay, I think we've covered the material. Let's move on to the next one, namely the car problem statement draft. I see the presenter is already online, and I will avoid inappropriately pronouncing your name. My apologies that I can't. Bruno, you bring up the car slides.
Thanks, Joel. Can you hear me, folks?
Yes, we can hear you.
Okay, great. Thank you. Hi, everyone. I'm Dhananjay Rao from Cisco, and I will be presenting on behalf of my co-authors and contributors on the BGP color-aware routing problem statement draft. This draft was also presented at IDR and BES. Next slide, please. The objective of BGP color-aware routing is to use BGP to establish an end-to-end intent-aware path across multiple domains, both IGP and BGP. An example of an intent is a low latency path. Next slide, please. A quick reminder, here in the Spring working group, there is a solution defined for interdomain intent or SLA-based path computation using SRTE. This is a mature and widely deployed solution. The solution document defines the notion of color to represent intent in the network control plane, and we intend to use the same. Next slide, please. We just see here an illustration of the color concept. An egress-p E3 tags a VPN route with color C1, expressing a request for a particular intent. Any ingress-p, such as E1, that installs this route will try to steer traffic for this VPN route through a path to E3 for color C1. Color is signaled using the BGP color extended community. Next slide, please. In the SR policy solution, the ingress-p E1 may request a SRPCE to compute the interdomain path, since the SRPCE is the one aware of the interdomain topology. The SRPCE will compute a path for that particular intent and return a label or a SID stack that the ingress-p will then install and use in the data plane. The rest of the network nodes are stateless, for this path. Next slide, please. Now here with BGP color-aware routing, we have the same automated steering, requirement as the SRPCE case. Only here the color-aware path is set up using a BGP hop-by-hop route distribution and best path computation. In this example, a route to E3 for color C1 is originated, say, from a border node 32, maybe redistributed from an IGP flex algo. It's propagated hop by hop across the domains till it reaches E1. At each hop, a best path is computed for that intent, recursing over the appropriate intra-domain color-aware path. A VPN route that is colored with C1 will then get steered via this BGP E3, C1 route. Next slide, please. Here we see an example of multiple intents. So for the same egress P E3, we have two color-aware routes, E3C1 and E3C2. They are independent routes, and may end up getting set up via completely different paths through the interdomain network. To complete the example, we have two VPN routes, one colored with C1, the other one with C2. Each route will respectively get resolved and steered via the appropriate E3, C star route. Next slide, please. When we come to looking at the deployment requirements, the reference topologies are well known. You can have multi-IGP or multi-AS designs, but a significant difference is the increase in scale. There are some networks where the scale can go into the order of hundreds of thousands of Ps in the network, and then we also have the case where we may need multiple intents to be supported in the network. Some common ones are listed here. We have best effort, but then there's low latency, two disjoint planes, and then an avoidance use case, perhaps with links, nodes, or domains. So just with this reference example, we see the number of routes in the network can go up to 1.5 million routes. Next slide, please. Here we just list a number of other intent use cases. The draft goes into detail in terms of illustrating the key ones with reference topologies. Next slide, please. The focus of this problem statement draft has been to have a concise technical analysis of the use cases and deployment constraints, and then enumerate the resulting protocol and design requirements. Some key ones to call out: of course, consistency with the deployed SR policy-based solution, as well as coexistence and interworking. A key here is the use of color to drive automated steering. We also extend the problem space. Intent-aware paths need to be supported in the VPN service layer as well, and needs to take into account NFV service chain integration. Next slide, please. There are a number of deployment requirements, but a key one is the setting up of paths across heterogeneous domains, where there's different technologies and encapsulations being used. Then the sort of the most significant one is the impact of scale on the on the solution, both on the data plane, especially where Mpls is used, as well as on the BGP control plane. So we clarify these aspects in the draft. Next slide, please. This work is the result of a collaboration with many people, both among the lead operators and vendors. So we acknowledge their contributions. We also recognize that there has been work in this area, specifically by the Seamless SR co-authors. We, as Shraddha mentioned, we reached out to them back in November, December, and there is ongoing effort to come up with a joint problem statement and for subsequent work. Next slide, please. Yeah, so of course this is ongoing effort, but we request review from the working group. Thank you.
Tarek, you have a question? Go ahead.
Hi, thanks for the presentation. This is Tarek with Juniper. My question is, there seems to be an assumption that the color has the same meaning when it's crossing multiple domains, has a uniform meaning. What is the guarantee that the same color means the same thing in multiple domains? Is there a need for translation, for example, do you think?
There can be a need for translation, and this is a key aspect that we call out in the draft, clearly defining the notion of a color domain that as differentiated from network domain. The draft goes into requirements that come out of it.
Tarek, this is Jim. Just to add to that, and I don't want to go down a rat hole, but that question is actually covered in the solution document, which is not part of these slides, so we can't discuss that. But if you want to look at that, go ahead and look at that solution document. I believe it's covered there.
Okay, go ahead, Linda.
Yes, I have a question. What's the difference between your color and the route target?
So firstly, a color is a construct that is used to represent the intent, and depending on the protocol being used, it would be signaled using different mechanisms. In the SR policy solution, to signal the request for that intent, the BGP color extended community is used to carry this color. Now, when it comes to BGP color aware routing, depending on the solution, it would be a particular BGP construct would be used to signal that color awareness.
So you will have another update or another instruction on how to forward the color, how to steer the color as separate. Is that correct?
I mean, don't want to go into the solution details since this was a presentation on the problem statement. But as Jim pointed, that there is a solution document, proposal that defines how color is used and signaled.
Okay, thank you.
Okay, Ran, go ahead.
Just a reminder that we have a draft solve the same problem. The draft name is Draft 2 IDR Interdomain LCU, and this draft describes the colored BGP-LU LSP, in which the routing prefix not only carries a label but also carries a unique color attribute, which helps to select the underlying logic slice. Please review and give us some comments.
Okay, Ran, may I suggest you type that draft name into the chat, because I doubt very many people were able to figure out what it was. So please type it, and I imagine the authors will go look. We're getting to the point we should move on to the next.
Actually, it might be better, Ran, if you could actually send something to the mailing list.
That would work too, yes.
Okay.
Sounds good. Thank you, Ran.
And now we go to the SRv6 Mpls interworking. Swadesh, I believe you're presenting this material.
Yeah, hi. I'm
Go ahead.
Yes, I will present. Yeah, hi. I'm Swadesh Agarwal, working for Cisco Systems, and I will present this SRv6 Mpls interworking draft on the behalf of all my co-authors listed here. And next slide. So this draft describes a solution for SRv6 and Mpls interworking. As we know, SRv6 is getting deployed in the customer networks, and we have a brownfield Mpls. So such interworking is a requirement. And this draft provides the simple building blocks to make this interworking happen. The initial version was posted in October 2018, and this is a Ref 5 which provides the additional details. The draft describes both the data plane as well as associated control plane procedures to achieve interworking. For data plane, this draft had introduced new n.dtm behavior, as well as it updates the existing n.bm behavior, which is defined in the network programming and which is used in this draft now. For the control plane, we go both into SRPC-based solution as well as the BGP-based solutions to provide such interworking. Next slide, please. So in this slide, what we'll try to do is we'll try to generalize the interworking problem into a simple problem in which I'm trying to show a central domain, which I'm showing in different example. It could be different. In this case, okay, the green is representing the SRv6 domain, and the orange is representing an Mpls domain, and the dashed oval represents an interworking function that happens on some border outer. Okay, so if you look at this draft, proposes two main scenarios. One is a transport interworking, another is a service interworking. At the transport interworking, what it means is our L3 or L2 services have a same control plane continuity. So what it means is, if you see the first on the right side first diagram, it says SRv6 is on the leaf, on the edges, and Mpls is in the central domain. So for simplicity, we have shown this, but it could be any cascading domains, any type of in any order also. But edge domains is in this case is an SRv6, and therefore they will have a SRv6 VPN services. Therefore, what we need to achieve is we need to tunnel the IPv6 or SRv6 traffic through this Mpls domain. So second use case for transport interworking is we have the edge, which is an Mpls, which runs the Mpls VPNs, and we have to transport this an LSP through the SRv6 domain. And the third one, that interworking scenario that we look is a service interworking, where the service, the L2, L3 services itself is SRv6 VPN services or BGP Mpls services that is shown on the edges as a VPN, as well as a SRv6 VPN and the Mpls VPN. And here, what we need to provide is we need to provide the connectivity for these L2 and L3 services through this interworking function. Next slide, please. So this draft defines a new n.dtm set behavior. What this behavior does is it decapsulates the IPv6 header and its extension headers, and then look the following Mpls packet top label in the Mpls table and forwards the packet accordingly. And this function is executed on the interworking box between SRv6 and Mpls domain. There's a pseudocode listed in a draft. I will not go through it, but it's just that after doing the decap, we look the top label we carried in the packet. Next slide, please. Also, this draft introduces the SRv6 and head-end behaviors. Here, what we say is we have introduced two behaviors. One is to h.ncaps, which is applied to an Mpls label stack. Here, when we receive an Mpls label stack, we push an IPv6 header along with the SRH. Together, the Mpls label stack and its payload becomes the payload of an IPv6 packet. And the next header field of an SRH must be set to 137. Also, there's a reduced version in which the first segment is not put in the SRH, but it is just put in the destination address. Next slide, please. Yeah, as I described earlier, we have broken the interworking scenario into transport interworking. What it means is we need to provide reachability to a locator if it is SRv6 VPN services, or to a LSP to a PE if it is an Mpls VPN. So this draft provides two mechanisms to provide such thing. One is a known as existing SRPC, which satisfies the intent across the multiple domain. Also, since SRPC learns the topology through BGP-LS from each of the domains, it is aware of the data plane discontinuity at certain interworking box or the border box. Also, this draft provides the best effort connectivity through BGP, where we advertise the PE locator or the Mpls LSP through such a discontinuity of network. Next slide, please. So for my examples, the way I will show is the green circle will show an SRv6 capable node. And here we will show a locator which would be represented by B:(K). K would be the node ID, and F is a function on that node. And the Mpls node would be shown with the orange, with the K represents their label would be the prefixed label, which would be represented by 16,000, and K would be the node number. And green and orange that I'm showing is a node which is both SR-MPLS capable as well as SRv6 capable. Next slide, please. So here I'm taking an example of SRPC solution to provide the transport interworking. Here node 1 and node 10 are running SRv6 VPNs because that's edge are SRv6 in this case. So now what happened, node 10, which is running an SRv6 VPN service, will advertise a VPN prefix with a SRv6 service SID, here which is shown as B:10 common tone DT4 because it's a VPN service, as well as color red because it's an SRTE based solution. And it has a certain intent. In this example, red is showing a low latency intent. Node 1 receives this update and node 1 doesn't know how to reach node 10, it will make a request to the SRPC to provide a low latency path, which is represented by color red, to the node 10. SRPC will compute the low latency path, and I'm showing its compute through node 2, 5, and 8. And SRPC figures out that there's a discontinuity of the data plane at the border node 4. SRPC installs the Mpls policy at 4 along the same low latency path till the node 7. And then that policy is installed on the node 4. As shown in the example, it has the segment 16,005 and 16,007. And it will again take you through a low latency path through the Mpls domain. But important aspect is that this policy is bounded to an IPv6 instantiation of a binding SID, which is n.bm, which is already described in the network programming, and we are using the exact same n.bm function here. And this segment, now SRPC will send this update back to the node 1 because that requested, in which one of the segments would be this n.bm behavior. So if you see the segments on the node 1, it takes through the low latency path through node 2, and then there's a binding SID for the node 4, and then through node 5 in that, and node 8. And if you see the packet that is received on the node 4, the packet that is received on the node 4 would be that n.bm function on node 4. And what that n.bm pseudocode is, it will update the next segments in the SRH as a destination, and then it will put a Mpls stack that is bounded to that policy and sends the packet out into the Mpls domain. And rest of the on the node 7, it will do a lookup of that IPv6 packet that is following the Mpls stack, and packet will flow to the back to the SRv6 network. Next slide, please. Exactly same procedures we can achieve for the SRPC for M/6. The difference here is our central domain is at SRv6. Therefore, the policy that SRPC will install on the node 4 here would be an SRv6 policy, whose segments would be again for the SLA part to the node 7, in this case again I'm showing the end function of node 5. And then important part is the last segment of this policy is a new behavior that we already described, is a DTM function, which causes us to look up the following Mpls header and send the packet further into Mpls domain on the right. And if you see that in this case, again, now SRv6 policy, the BSID is represented by an Mpls BSID, and that SRPC will install on the node 1 as one of the segments which will cause the stitching or the interworking function on the node 4. From the packet path point of view, on the node 4, I will receive the packet with an Mpls BSID. It's shown as 30,007 here, which will push an IPv6 header with the destination as the first segment as a node 5, and then the next segment would be going into an SRH, which would be a DTM function of node 7. And on node 7, once we hit the DTM function, it would see it will hit my SID table because the locator is of the node 7, and it's a DTM type, and the next header would be 137. So it will do a lookup of the top label, which is 16,008, and it will forward to the next segment, that is node 8. Next slide, please.
Before you go to the next slide, Dhruv is trying to ask a question. Go ahead, Dhruv.
Yeah, thanks, Joel. Swadesh, with my PC chair hat on, I would request you to talk to the binding SID authors. It's a working group document. We think it's going to be ready for working group last call as well. So what you are describing seems to be supported. There is no limitation there that for SR path, SR MPLS path, you can have a binding segment which is both SRv6 binding segment or an MPLS binding segment. So it seems to be allowed, but I would prefer if it is made explicit. So it is that you have a use case for this, and I think it's a very valid use case. So maybe just talk to the binding SID authors and add one statements there so that it is very clear. Second comment I would have is we also have multi-domain case that we handle in PC quite well, and most of your document is focusing on a single PC that is taking care of all the domains. So just think about even handling inter-domain aspects as well. Thank you.
Sure. Thanks, Dhruv. I will talk to for the both binding SID as well as the other aspect you mentioned. Sure. Okay, next slide, please. So here we have described both the SRPC solution for 6/M and M/6. Something similar we can do for BGP-based in transport interworking. So here we know edge domains are SRv6. So our services would be SRv6 VPN services. So what we need is when the node 10 advertises such an SRv6 VPN services, and node 1 needs a reachability over the central domain for the PE locator, because the SRv6 services would be advertised with an SRv6 service SID, which would be the locator of node 10. Now, this reachability is like an IPv6 reachability over an MPLS domain, which is already supported like a 6PE functionality. And so therefore, we can use exactly same functionality when an IPv6 prefix is advertised through node 7 to node 4. It would be with a label BGP IPv6 LU address family, and it would be transported over an SR MPLS intra-domain tunnel, whatever it is. Next slide, please. So next one come our edge domains is MPLS, and our central domain is SRv6. So what happens today in such is this is running an BGP MPLS VPN. So what we need is we need a reachability from node 1 to node 10, which is an MPLS LSP. What today existing mechanism is a BGP 3107, which cause the label cross connects wherever we do next hop cell. So in this case, on the node 7 and on the node 4, and there would be a cross connect for a loop back to node 10. So exactly same mechanism would be used. The extra step that would be required would be, instead of tunneling from that BGP LSP from node 4 to node 7 over an MPLS LSP, we will tunnel that into an IPv6 tunnel whose destination would be of the behavior DTM, n.dtm, which is already described. And that what node 4 is supposed to do is it need to do a label swap as it does today on the node 4. In addition to that, it will put an IPv6 header whose destination would be n.dtm, and put that send with an IPv6 encapsulation to the node 7 with it would be of the DT, and the behavior of that destination would be of the DTM type. And on node 7, what will happen is since it's a DTM type, we will decapsulate the IPv6 header and its extensions and do a lookup of the next label which would be again the BGP LU LSP label, and packet would be reaching node 10. So this draft also proposes carrying this n.dtm function as an SRv6 SID in the BGP LU update, and we have added a new TLV for carrying that update. Next slide, please. So till now we were talking about transport interworking. So there is a use case of interworking in which we have to make a control plane which is running SRv6 VPN and the MPLS VPN. So for that, we propose there's already a gateway solution. A gateway is a box which supports both the SRv6 VPN as well as MPLS VPN. And what happens on this box, we do a service termination. So that means there's a L2 based on service, whether it's a L2 service or L3 service, there's a lookup involved. So that terminates both the underlay as well as overlay, and therefore we can provide the interworking using a gateway solution. Next slide, please. Yeah, so we have covered in this draft. We have made sure there are building blocks being taken care, and these building blocks cover all the complex interworking scenarios. And therefore, we would like the working group to review this as well as adopt this document. Thank you.
Questions for Swadesh before we move on to the next one, which is a different n.dtm. Okay, hearing no questions. Ron, you have the floor. All right, Daniel, you have a question. Go ahead quickly.
Just last minute question, but that was the point I was trying to do with Shredder on her presentation, because I see some similarities, although Shredder, you seem to be very focused on defining the problem, but there's a piece that in here, what was just presented, that is also referring to defining a problem. So I was just wondering if this work should, start from the beginning to looking at merging or contributing instead of waiting that we're too far along and then end up with two different ways of doing the same thing.
Sure, Dan. We can discuss and see how to go ahead with it. Yes, sure. Yeah.
Thanks.
Thanks, Dan.
Can you hear me?
Yes.
Okay.
Bruno, you.
Okay.
Yeah, you have the next one up. Go ahead, Ron.
This is Ron Bonica, and I'm presenting EndDTM on behalf of my co-authors. And to maximize confusion, the EndDTM is named exactly as the same as the EndDTM that you just heard about. It has many of the same functions, but a few small differences. Let's go over them. First slide. Okay, this draft introduces a new SRv6 endpoint behavior called EndDTM. It's for interworking between SRv6 and SR-MPLS. And like any endpoint behavior, it contains a function plus arguments. The function causes the processing node to de-encapsulate a packet, that is, to remove the IPv6 header and all its extensions, to impose an SR-MPLS label stack, and to forward the packet as per the MPLS label stack. The arguments determine the label stack contents and anything that might be encoded in the label stack. Next slide. Next slide. Okay, here's a typical use case. We have an SR path that goes from node 1 to node 5. There's an SRv6 part that has nodes 1, 2, and 3 in it, and an SR-MPLS part that has nodes 4 and 5 in it. Node 3 is the one saddled with the task of translation. So node 3 has to be both SRv6 and SR-MPLS aware. 1 and 2 are only SRv6, or only need to be SRv6. Node 4 and 5 only need to be SR-MPLS. Next slide. So how do we process this? And here is where you'll see the difference between the EndDTM you just saw and this EndDTM. If segments left is greater than 0, we discard the packet and send an ICMP message to the source. If it is not 0, we do nothing until we're processing the upper layer header. When we process the upper layer header, we de-encapsulate the packet. We push an MPLS label stack that is associated with the DTM arguments. We set the MPLS traffic class and TTL to reflect the traffic class and hop count that was in the IPv6 header. And we submit the packet to the MPLS lookup for transmission to the new destination. So there are two big differences between this EndDTM and the one you just saw. One is that we allow any payload, not just MPLS, and the other is that we make a point of setting the MPLS traffic class and TTL values appropriately. Next slide. The next steps, we're asking for working group review and a call for adoption. We've heard a request from Dan to talk about merging solutions, so that probably has to happen too. And that's it.
Okay, there's a question from Swadesh and from Daniel. Swadesh first.
Yeah, hi Ron. So isn't what you are proposing is when we receive that function and its argument, you have to put an MPLS stack based on the arguments, correct?
Yes.
So isn't that n.bm that is already defined in network programming? It's just that it's a decap variant of it. I'm just like,
yes.
Because today
it's very
network
close.
Programming.
Very close. It's very close to n.bm.
Yeah, that's what I'm saying. It's your lookup function and arguments already give you what SID stack to put, and that's the difference between n.dm, where we are proposing to do a lookup into whatever is falling in the MPLS header, and that lookup will give you MPLS stack. Here,
okay, yes.
So
there is a.
So I'm saying this is in some sense n.bm. It's just a decap variant of it.
It's very close to n.bm. Also, the MPLS stack may not fit in the arguments. So it may be that some implementations have to do a lookup. The draft is silent on that.
Yeah, but from my point of view, I just looking at it, I felt this is an n.bm. That's what I want to point out. No, thanks.
It's very close.
So my question, Ron, visual, I'm assuming I'm free to go. So,
yes,
Ron,
go ahead, Daniel.
It's close to that BM, but it's not quite. Ron, are you gonna propose a new end function, or
yes,
you're going
that's
to be
exactly
close
what we're
enough?
doing. We're proposing a new end function.
So yeah, I have the same comment. Can we look at merging before the chair stick comes in and then we end up with the design team?
Yeah, that's a conversation to have. Probably not in the next 3 minutes, but let's have it.
Good, thanks.
Thank you. Cheng Li, you're next.
See these two documents define the same thing, and I could like to see the end of this story. And by the way, GSIV6 for Mpls also define a similar mechanism. So maybe we can combine these kind of things to discuss in the mailing list. Thank you.
Okay. Any further questions? Hearing none, we'll move on to the next presentation. Zafar, I believe you're going to be presenting building blocks for SR building blocks for slicing in. You don't need to put yourself on the queue, just.
Oh, so I'm here. Okay, good. Many thanks.
Yes.
So I'm going to present this draft on building blocks that are needed for creating slices in SR network on behalf of my co-authors. Next slide, please. Okay, so let's first look at the scope of the draft. This draft is an informational draft. It lists essential building blocks needed for network slicing. It basically explains how these building blocks work together as independent pieces and work seamlessly to provide scalable slicing solution and solution that are defined for incremental deployments in mind. Next slide, please. A very brief history of the draft. We started the work in July 2018. The Ref 2 was presented in IETF 106 in spring. Next slide, please. So in the Ref 2, when the presentation happened, we covered the following building blocks. The SR policy, which enables steering of traffic along an arbitrary path. That arbitrary path may be low latency path or a path that avoids certain resources. ODN use case allows service traffic to be carried on paths that meet customer or application SLAs. Automatic steering is possible into network slicing using that construct. Then we talked about flexible algorithms. They complement SRTE policy solution by adding new prefix segments with a specific optimization objective and constraints. So it allows, so this is an example of why we call them independent cooperating building blocks, because SR policies are supported with or without Flex Algo. On the other hand, Flex Algo leverages ODN and automatic steering construct of SR policy. Then we talked about TI-LFA, which plays a role in providing order 50 millisecond protection in the underlay. As these are the building blocks that work together, the way that, say, for example, TI-LFA and Flex Algo works is that the backup path for TI-LFA is expressed with prefix SID of a specific flexible algo. The backup path is optimized per Flex Algo. So we don't have cases where traffic for a Flex Algo, which is low delay, can be back up on a path that are not delay optimized path. Then we have VPNs that provide means for creating logically separated network to different set of users to access the common network infra. Then service programming provides supporting orchestration of virtualized service containers, and is fully integrated with SR policies. This is how the building blocks work together. O&M PM provide useful means for collecting topological and service data that is used for implementing slicing. And then we have IP-MPLS disk serve architecture that enables network devices to provide differential treatment based on EXP or DSCP marking. Here we would like to draw attention that QoS works independent of topology or routing. And then slice orchestrator puts things together as the management plane. Since that revision, we also now added references for stateful slice ID. These references, so later on when we go through this, we're going to go through this, how the stateless slice ID fits together as a building block that does not disrupt the picture from routing point of view or from topological point of view, but works to provide additional differentiated treatment. So next slide, please. So let's have a look at few attributes.
Zafar, before you go to the next slide, we have a couple of people who apparently have questions about the history that you've presented. So Greg, you're up.
Maybe I can finish this and then we can take question. I think it's not so important.
Hi, Zafar. I have a question. So which definition of the network slice this refers to? Is it 3GPP network slice or IETF network slice?
Could we wait so that you are clear later on? Once I do can we come back to this once I'm done with the presentation?
Well, I think it's a basic, very fundamental question because we need to understand the context of what the network slice we're talking about.
Let's wait. I like you to understand the solution and then I can.
Without understanding
Greg, we have to let him, at this point, I understand why you're asking, but we have to let him continue at this point if he thinks the rest of the presentation may clarify it.
Yeah. Okay. So
go ahead.
Next slide, please. So in the context of the attributes needed to create a slice which is independent of routing and topology. So one of the attributes of slice ID for differential treatment is that it's supposed to is to be independent of routing and topology. What does slice ID does? What slice ID does? So in this picture, we have a picture on this slide. We have a picture on the right that shows queuing treatment given to two slices, slice 1 and slice 2. And these two slices, there is some information that is in this picture. The green slice is identified by slice ID 1, and the blue slice is identified by slice ID 2. Traffic that the green and blue slices carry is aggregated using hierarchical queue. So it is not possible for green slice EXP0 traffic to disturb blue slice EXP0 traffic. And what other attribute that we like is that slice ID should be independent of routing topology. It should be stateless, and it should be done in a backward compatible fashion for incremental deployment. Next slide, please. So now let's take a look at exemplify why slice ID construct needs to be independent of routing and topology. So I like to draw your attention to the picture on the right, which ignore the big box in that picture for now. Here, within that, you have a network with two flex algo. Low latency flex algo orange 128, and low cost flex algo red 129. I did mention earlier that if you have a failure, let's say if you have a failure between link 1 and 2, then what you like, because the low latency slide traffic, you like the low latency traffic to use backup resources that are also, or backup path that is also low latency optimized. And indeed, this is what happens for flex algo case. So if there's a failure between on link between node 1 and 2, then the traffic is diverted to a low latency delay path, which is shown by orange. Now, it makes sense to extend this to the differential treatment that the slices provide. And in this case, now let's take this picture, which is half blue, half green. And this is like that because it's a common infrastructure or a common flex algo. So we are not replicating flex algo per slice ID, but reusing the same flex algo. Again, topology and routing independence is important. Using the same instance to create differential treatment. Now, what happens when you have a failure in the same link, node 1 and 2, but now slice ID 1 and slice ID 2 traffic that is going over that link 1 and 2 is disruptive. You redirect traffic through 4, 3, and 2. So we are going to focus on node number 4. When node number 4 receives the packet, and packet is a stateless instance of slice ID in the packet. So when node number 4 receives the packet with slice ID 1, obviously it applies the differential treatment given and reserved or programmed for slice ID 1. When the traffic comes for slice ID 2, then it gives the same differential treatment that that is programmed at node number 4 for slice ID 2. So in this fashion, you really made the TILFA, flex algo, and other building block completely transparent to the differential treatment that is required for slicing. Slice ID really act like a QoS, which is independent of routing and topology. Next slide, please. So regarding the seamless working of these building blocks, we saw that flex algo, how it works. It's the same thing, like you have a construct which is a differentiated treatment on a node. But you don't need too many instances of that differential treatment because you have other constructs like VPN, policies, QoS differentiation that make you scale. And on a device, you're not going to have too many behavior for differential treatment. So this is how the slice is scaled. Next slide, please. So we're going to take an example. This is with the reference of how stateless slice ID information is carried for SRv6 network. And in this picture, we have an SR domain, and we show that traffic is in green. Payload is supposed to be classified into green slice, and a blue payload is supposed to be classified in the blue slide. So we're going to focus on SR node ingress 1, which always encapsulates the packet in an outer IPv6 header, an optional SRH. This node, this node may classify the packet. So when the green packet comes, then it will be classified into green slice ID. And then the green slice ID is carried in the 8th most significant bit of flow label.
Zafar, can you possibly pick up the pace? You've spent rather more than your allotted time already, and we do have some more questions.
Sure. So good. So basically, then what happens is at node number 2, which is a transit node. If it's slice aware, then it look at that field that is in the packet and apply the differential treatment that is programmed at node number 2. If it is not aware of slice ID treatment, then it just forwards the packet without any further differential treatment using other building blocks, or we can call it forward the traffic using the default sleep. So that enables the difference. That enables the incremental deployment. Next slide, please. So now for the MPLS draft, there is a draft that Bruno presented to MPLS working group. It works for both segment routing and non-segment routing MPLS, and is similar to what the other reference I just went over. The exception is that the slice ID is carried in the entropy label, and the TTL of the entropy label is where slice ID presence indication is provided. A node that is capable of doing the differential treatment, apply the differential treatment. Other nodes work seamlessly and provide load balancing using that flow label, entropy label. With that, I would stop here. Next slide, please.
Let's just take questions.
This is the last slide, so I stop here. And basically, we would like to get feedback from the working group, and would like working group to adopt the document.
The questions.
Yes.
Xidong, you're up.
Yeah, this is Jiedong. My question is first, the first part of this document presentation is a good summary of the SR mechanisms which have been defined in this working group. To make it more network slice specific, perhaps I suggested to reference the resource-aware segment and SR for Vpn+ drafts, which are also the working group documents in Spring working group. And the second comment is the sharing of topology between multiple slices was proposed in the scalability consideration draft in TIS, which hopefully I can present in the end of this session. And the last comment is for the data plane slice ID mechanism. In my understanding, this is based on the IPv6 data plane or Mpls data plane extensions, which will belong to that relevant working groups. Okay.
So many thanks for the comments. So I agree. We can work offline on the suggestions that you made. And this is an informational document. This document does not.
Sorry.
To the document. So.
Zafar, I'm going to cut in here. We've got literally not much time left. We've got one presentation left on the agenda plus 2 that are there if we have time. Well, we're going to run out of time. So
sure. Thank you.
I think we need to cut the queue with the people on here. Let's get these questions through quickly and move on, please.
Yeah, and quick answers.
Thank
please.
you. I will follow up, Greg, with you offline or on the mailing list. Thank you.
Greg, you're ahead of the queue. Go ahead.
I didn't understand. Are we cutting the queue?
No, the folks on the queue can go. But
okay, then I dropped by mistake. Can you give me a chance? I dropped out by mistake.
Thank you for
2 quick points.
Go ahead.
I listened for the whole presentation, and still I don't understand to which definition of network slicing this proposal is applicable to. And another one is just minor nit that EXP field in MPLS label element has been renamed traffic class for 10+ years. So just please use the proper identification. Thank you.
Yeah, an answer to that on the list or other discussion. Cheng Li.
Sure, thank you.
Cheng Li, you're next.
Do you really think 8 bits is enough for a slice ID and like for also for Mpls, SR Mpls? is it appropriate to use the entropy label? Because each node we try to parse the whole seed stack, get the entropy label. So what's your opinion on that?
Sorry, Cheng, this is Jim. Please take that one to the list. If they're comments, please give the comments quickly, then we can move on. If they are actual technical questions, please do it on the list.
Sure, let's take
Tarek?
it on this. Thank you. And,
Thank you.
More for Bruno, that comment. Thank you.
Thank you. Hi, this is Tarek. You didn't number your slides. I can't tell you which slide to go to. I'll tell you what I remember you flashed on the slide. It was about a slice is independent of the topology. In fact, there are requirements that a slice can be steered or should be steered on certain topological elements. I'll give an example. You want secure links, or you have diversity requirements, which are under discussion in T's working group. A slice has topological dependency. It's not independent. I don't know which slide you were, maybe the previous one or this one. You're saying that it doesn't have any.
We could use this one. We could use this one.
The previous one, I think, also had same comment.
I think.
Yeah,
I think this is a topic that needs more discussion than we can get through in this time. Your point is valid, Tarek, but it needs to be discussed on the list. Daniel, you're the last one, and then we'll go back to Tarek for his, not to Tarek, for, go on, Daniel.
So, Greg, about the question about the definition of the slicing that you had, I know that someone from Huawei Robin sent an email with like in this working group on the test one that is about like 8 different documents attempting to come up with a definition of slicing. I read them all, and in this document here that Tarek is just a presentation. If we zoom out a little bit, especially with that slide or the one previous, we're talking about the fundamental block. And I don't think when you look at those fundamental blocks here, that one, exactly that one, it violates any of the attempted 8 different documents of the definition of slices. I don't think it violates that, even though if the meaning of the slices is not that really clear. I think those building blocks are still required, and that's pretty much how I see it myself as a co-author when I'm thinking of designing in an org that requires end-to-end transport slices across the backbone. But the point is valid. Perhaps we could have a summary of the definition of what's a slice added to this one, or having a reference once we make up our mind about what's the real definition of a slice. And maybe I can, Jeff, you were behind me, but I'm pretty sure you wanted to highlight the definition of slices if we still have the time on the chair.
No, we're out of time. There is a lot of work going on defining slicing. To the degree this is a definition independent building block, that's great. To the degree it's definition dependent, it needs to be clear about the definition. That the relationship needs to be clarified in the draft and be discussed on the list. And with that, we move on to Tarek's presentation.
I don't see the slides yet. Hello, this is Tarek, and today I'm going to give you an update about a solution to realize network slicing over an SR network. I am presenting on the behalf of the co-authors. I'd like to thank all of them. Next slide, please. So I'll give a timeline or a history of the updates on this draft, and then I'll dig into the maybe a review or recap of the solution we're presenting, and then close off with the next steps. Next slide, please. So timeline, revision 0 was introduced as a companion document to the solution document we presented in TEAS, and it describes how we can realize this solution in an SR network. Rev 1 included updates to align with certain terminology that we added in the base document. And we addressed feedback from working group members. We thank them for that. And we have new co-authors who have joined our work. Next slide, please. So these are key terminologies. I'm not going to go word by word in details. I'll just high level mention that the slice policy is a means to install a set of rules on a network element so that we can realize a slice aggregate. and I'll let you read through these terms offline. And I'll be using the slice policy in subsequent slides. So next slide, please. So very high-level overview, a router that is going to process a slice aggregate packet will require to do a number of things. The first is to identify the packet belongs to a slice aggregate. That's number one. Number two, we need a way to select a next hop to forward the packet on. And this is determined by the topology of the slice and the optimization criteria that we are seeking. And the third rule that we need to enforce is the forwarding treatment. This is, maybe a certain percentage of the bandwidth on a shared link that you want to assign to a slice aggregate. So all these rules are part of a slice policy definition that we are introducing in the base document. On the right-hand side, I'm just showing high-level structure of that slice policy definition. Next slide, please. So we are presenting two approaches to realize the solution in an SR-capable network. The first one is by associating a slice aggregate with a SID, so that packets using those specific SIDs will get the identification or association to the slice aggregate, as well as the forwarding action, the next hop selection. So the extensions to advertise the slice aggregate prefix and adjacency SIDs were presented on Tuesday. There's a pointer to the draft. The second option we are proposing is carrying a separate ID in the packet. So this is very similar to what you've seen. Zafar talked about it. We are part of that work, and we have proposals there. So the idea is to carry an identifier that will associate the packet to a slice aggregate. I'm putting 3 pointers here just for reference. The working groups, the respective working groups, are still working out the details on which proposal is the best, but we are advocating this proposal as well. Next slide, please. I'll go with the first option that we are presenting to realize the solution. As I said, we will advertise SIDs associated with a specific slice aggregate. So the forwarding action in that case is dictated by the top or active segment, be it the prefix or adjacency. The topology is defined by if it's a prefix SID, it carries a empty ID and a flex algo number, and the FAD will dictate the topology that is used to select the next hop. The forwarding treatment is a rule part of the slice policy definition, as I mentioned in the earlier slide. Now, some scale impact to this proposal. We are not proposing a flex algo definition for a slice aggregate. So the same flex algo definition or multiple slice aggregate can use the same flex algo definition. This is a good point. Other proposals are advocating a flex algo definition per slice or per slice aggregate, whatever the term would be. The second point is the IGP topology can be shared among multiple slice aggregates. It can be, and that will allow better scale. The computed path, result of the optimization criteria, can also be shared by multiple slice aggregate SIDs. Next slide, please. So this is an example where a packet is carried by a top SID that is associated with a slice aggregate. I have SA1 packet with a top SID is 16,005, and SA2 packet with 17,005. Both of them are destined to node 5. On any transit node, let's assume it's 3, we have a slice selector which will put the packet based on the top active segment into the respective queue, and then there is a hierarchical queue there that you can apply differentiated treatment based on the EXP as well. But the high level, what I want to share here is that the top active segment is the one that is used to identify the packet or associated with a slice aggregate. Next slide, please. The second option is carrying the slice aggregate selector or ID in the packet. The forwarding action in this case is determined by the top active segment, whatever the top active segment would be. Next stops are computed as usual by IGP based on the topology and the optimization metric. The forwarding treatment, as I mentioned, is part of the slice policy definition that we install. And in terms of scale impact here, we are reusing the SIDs. So multiple slice aggregates can use SIDs that are defined or instantiated in the network. They are not specific to a specific slice aggregate. The FAS can be shared by multiple slice aggregates based on the topology requirement. Again, the second bullet is about the topology can be shared. And the last point is that the computed path, as a result, can be shared by multiple slice aggregate packets, depending on the top active segment. Next slide, please. Here's an example where we have a packet destined from, let's say, 1 to 5. And you'll notice the top active segment for SA1 packet and SA2 packet both have the same segment routing SID, 17,005. The selector in this case is carried in a different field in the packet. I did not put details because there are multiple proposals there. One of them was mentioned, the entropy label, encoding it in the entropy label is one option. But the selector can be simply in the packet, and it will put the packet in the specific slice aggregate queue, and we can achieve the same hierarchical treatment that we are after. That's what I want to see on this slide. Next slide, please. So we welcome feedback on this proposal. We think this will allow us to realize the solution in SR with the automation required with the slice policy. The automation, we are providing the ease of instantiation of a slice aggregate in the network. I would love to answer any questions that anybody has.
Okay, Jibo. Jibo, you put yourself on the queue. If you have a question, please speak up.
Hi, this is Zibo from Huawei. The multiple slice is the same topic. The solution can use per slice SID or the slice extension in that plane. This solution has been proposed in SR for VPN Plus and VTN Draft in 2019 and earlier 2020, respectively. The slice aggregate ID is the same as the VTN ID. I think it's no need to this work. Thanks.
Yeah, my feedback on this, we are aware about this VTN proposal. We did talk to the authors and we had a chance to talk about it. There is an email thread that was started. We think the slice aggregate has some key differences to a VTN. And we would like to take that discussion further. If there is any alignment that could happen, we are welcome. We would welcome that. We're happy to do it.
Okay, Jidong.
As we discussed in the TIS working group, the terminology consistency will be important for people to understand and compare the solutions. And then, since this is a SR-specific document, one comment is the SA-specific SID a kind of resource-aware segment?
I didn't catch the remaining part.
So the second half of this question was to note that the SID you're defining here seems to have some significant similarity with the adopted resource SIDs that we have. And let me save some time. I think we need to sort out the relationship and tune both of them to get there.
Okay. So G, I acknowledge the first part. We will follow up. On the second part, there is some key differences between SA SID and resource-aware SIDs that at one time you were not proposing extensions to associate a SID with a slice aggregate or a slice. I don't know if that changed. We can take a look. No problem. There were no protocol extensions originally.
Last topic, Zafar. You get the last question, Zafar.
Okay, so Tariq, my question is that when you use MPLS label to carry the slice ID, can you comment on the backward compatibility, like if you have a device in between the two nodes that are participating, and what happened? Do you need all nodes to be upgraded?
Depending on the solution that there are multiple solutions that we are presenting, depending on which working group you mean. We would like the solution to be backward compatible such that a slice aggregate packet traversing a node that doesn't support that capability, the packet will be forwarded still. And it might not get the forwarding treatment that it's after, but it will not be dropped.
And other than the entropy label usage, I was specifically talking about the option where MPLS label or top label carry the slice ID.
In any solution
I understand
that we
with Bruno's draft, I understand. And that's what I was talking about, backward compatibility in Bruno's draft. But my question was for the other draft.
There are multiple proposals. My answer is there are multiple ways to carry the slice aggregate IDs. One of them is inside the entropy label. Other ones are there. I left pointers, and backward compatibility is required in all.
Yeah, it'd be good to see that description in the draft. Thank you.
Okay.
Yeah, sure.
Thank you all. It has been a set of interesting discussions. I wish we had more time for more of the discussions. Please take them to the list.
Just one comment. We had two presentations, if time allows. For your information, they are scheduled in other working groups, so you can have a look. For example, for associated channel over IPv6, there is a presentation in RTG, WG tomorrow. And for scalability consideration for VPN Plus, there is a presentation in TEAS. Actually, it was yesterday. Thank you.
So thank everybody thank you all for your time. Okay.
Bye.